This lesson will focus on the takeoff climb requirements for Class A aeroplanes in the commercial transport category. The takeoff climb, or takeoff flight path, extends from 35 feet above the takeoff surface to 1,500 feet above the takeoff surface. However, with a contaminated runway takeoff, the takeoff climb begins at 15 feet and not 35 feet. The point on the ground directly below the 35-foot screen is called reference zero. There are two main requirements that must be met within the takeoff climb, and these requirements are based upon an engine failure occurring at VEF. Remember that performance of Class A airplanes must account for engine failure in all flight phases. The first requirement is that the airplane must be able to achieve the minimum climb gradients, and secondly, the airplane must be able to maintain sufficient obstacle clearance. Remember that the climb gradient requirements are air-based gradients, and the obstacle clearance requirements use ground-based gradients. When assessing compliance with the regulations, the manufacturer or operator may either use a continuous demonstrated takeoff climb or a segmented takeoff climb. Segmenting the takeoff climb does make the requirements and the procedure a little easier to comprehend. Therefore, we will use a segmented takeoff climb profile, as do most operators and manufacturers. The takeoff climb is generally split into 4 unique segments. Each segment is characteristic of a distinct change in aeroplane configuration, speed, and/or thrust, with various actions and climb gradient requirements. Generally, there are 4 segments, and you will need to learn what unique characteristics define each segment. The takeoff flight path starts once the takeoff is complete, in other words, at 35 feet, with the aeroplane at V2 with one engine inoperative. The 35-foot screen marks the start point of segment 1. The objective at this point is to climb, as expeditiously as possible, which is difficult because of the lack of excess thrust due to the large amount of drag created by the gear and flaps and the fact that only one engine is in operation. Therefore, the strategy is to retract the gear and flaps as soon as possible. Since retracting flaps at low speeds close to the ground is dangerous, the only option is to retract the gear. Once the gear is up and locked, then the first segment is finished. During this segment, the steady gradient of climb must be positive. The second segment starts at the end of the first segment, i.e., when the gear is up. The objective now is to retract the flaps. However, flap retraction is not permitted below 400 feet. Therefore, the action by the pilot is simply to climb, at no less than V2, until 400 feet is reached. Once 400 feet is reached, and flap retract can commence, segment 2 ends. Since the aeroplane has had the main source of drag removed, the minimum gradient requirement is more severe at no less than 2.4%. Segment 3 starts above 400 feet, and is the flap retraction and acceleration segment. However, retracting the flaps will increase the stall speed. This reduces the aeroplane's safety margin. Therefore, the aeroplane must accelerate during flap retraction from V2 to the 0 flap speed, and then to the final takeoff speed. The final takeoff speed is also called the final segment speed, and is intended to be the one engine inoperative best angle of climb speed. Once this has happened, thrust can be reduced from maximum takeoff thrust, TOGA, to maximum continuous thrust, MCT. In fact, maximum takeoff thrust is limited to only 10 minutes. Therefore, acceleration and flap retraction must be complete by then. The acceleration phase of this segment poses a climb problem. To climb, excess thrust is needed. However, accelerating the aeroplane also requires excess thrust. Therefore, it is not possible to adequately accelerate and climb at the same time, and, as such, segment 3 can be flown level as shown by the illustration. The fourth segment starts when the flaps are retracted, the final segment speed is achieved, and the thrust is set to maximum continuous thrust. From this point, the aeroplane is climbed to above 1,500 feet, where the takeoff flight path ends. The pilot will either rejoin the airfield to land, or continue en route to the takeoff alternate. The climb gradient for this last stage must not be less than 1.2%. One last point. The gradient requirements for Class A aeroplanes with more than 2 engines form part of the syllabus, and therefore they need to be remembered as well. Although we have already mentioned it in the previous lesson, the climb limit mass tells us what the maximum mass of the airplane can be in order to achieve the minimum gradient requirements. Having a mass greater than the climb limit mass would mean that the airplane will not have sufficient performance in the event of engine failure to achieve the climb gradient requirements. The graph to calculate the climb limit mass is in section 4 of CAP 698. We have worked through an example in the previous lesson, but nonetheless ensure you are confident in being able to use this graph. The introduction to the climb section, shown on the previous page, reiterates the climb requirements, and it states that during the takeoff climb, the aeroplane must A. Attain the most severe gradient requirement of the takeoff net flight path, and B. Avoid all obstacles in the obstacle accountability area by the statutory minimum vertical interval. Both these requirements have already been mentioned in the introduction section of this lesson. The climb limit mass deals with point A. In other words, being at or below the climb limit mass guarantees attainment of the most severe gradient requirement of the takeoff flight path. What is the most severe angle of the takeoff flight path? Well, shown on screen is the takeoff flight path and segments of the takeoff climb. The most severe gradient requirement is in segment 2, which for a twin-engine jet aeroplane is 2.4%. Therefore, the climb limit mass ensures that the aeroplane, in the event of engine failure, is able to attain a 2.4% gradient or more. Remember that these climb gradients are air-based and therefore independent to the effective wind. Looking through the climb limit mass graph confirms this, since there is no account for wind.